Okay, I think we should get started. Hello, everybody. Welcome back after this short break. Hope everyone had a good mid-autumn festival. Got to go home, eat some good food, at least have a good family time. So I wanted to first start up with some administrative thing. I think most of you have or may have heard that some of the classes are resuming limited capacity to be, or at least there's a consideration of possibly doing classes offline again. Um, and I think even some of you have asked me this question, whether there's any chance of the classes being in person again. So my personal opinion is that I think for the time being that we should avoid doing too many of these face-to-face meetings. I know that it is a much better way of teaching. Honestly, I prefer to see everyone in class as well, but I do think that for public safety reasons, I think we should limit the amount of offline events, classes, and everything. So unless you hear otherwise, please assume that the classes remain online and that even includes examination. Okay? If examination, especially the one towards the end of the term, is going to be in person, then of course I will make sure that this is announced well ahead of time. But for the time being, especially when the second, third, or even the fourth, whatever you want to call it, wave is coming, especially when the flu season starts to hit somewhere in October, November, then it may be difficult to justify offline teaching. So again, for the time being, please assume that all teaching will remain online. In fact, all activities remain online as much as possible. Okay. Are there any questions about this? Okay. If not, then we can move on again. I do ask everyone who is in the class here to make sure that your screen name is something that we can recognize you with. So please do change it to your real full name so that we know how to identify you. Okay, excellent. Okay, let's get started. And since this was a bit of a longer than usual break, let's take a little bit of time to go through a recap of what we've done. So recall that we started off our discussion last time by actually considering the so-called Laplace equation. Okay? And the reason why this is important is because when we consider the potentials of the electromagnetic fields, then it actually turns out that both of them are governed by Poisson equations. Okay? So we take a look at the potentials, so the electromagnetic potentials. They're governed by Poisson equations. So we have for the scalar potential, we have that this is minus rho epsilon naught, and then for the vector potential, we have that this is minus mu naught j. Okay. Now, of course, if we are in vacuum, these simply turn into Laplace equations like this. So the importance of Poisson equation and the Laplace equation are, as you can see, are paramount. Because once you have the potentials, again, this stems from Helmholtz theorem, then once you have the potentials, you can fully specify the electromagnetic field, right? The electric field using the scalar potential, the magnetic field using the vector potential. And so indeed, we looked at the Laplace equation, and in particular, we arrived at the notion that the Laplace equation is a second order partial differential equation, which is then governed by, or at least the solutions are governed by the so-called boundary conditions. Okay? So indeed, if we look at the, let's look at the Laplace equation, which is just a second order PDE. And so the boundary conditions, so the boundary conditions are important. We started off with a relatively technical discussion where we make distinctions between a Dirichlet condition, which is, well, let me see if people paid attention. So we've got Dirichlet, we've got the Neumann, and we've got the Cauchy conditions. Do people still remember what they are? So for example, the Dirichlet condition, what does that say? Anybody? It's a technical term, so it's not too important, but the Dirichlet condition says that phi, the field that you're considering, yes, indeed, phi is specified, is some function f at s. Okay, and the Neumann condition is similar, but instead of the values itself of the field, we actually have that the normal derivative is some function g at s. Okay, so in this case, it's the derivative normal to the surface is specified everywhere on the surface. And then the Cauchy condition is that both the values and the derivative are specified at s. Okay, so this is pretty much where we started off, and this is, as we'll see, this is important, right? We need to be able to specify the boundary conditions in order to solve, the problems of both the Poisson equation and the Laplace equation. So the next thing that we looked at is the actual electrostatic boundary condition. So what are they? I hope that, that to a certain extent we still remember. These are the boundary conditions. Okay. And so we calculated them by looking at a particular surface where there's either some surface charge density or there's some current density over some surface. And then using the two theorems that we know, so this is Gauss's law. This is for Gauss's law and basically Stokes' theorem where we go around in the loop. So knowing what the, both the curl and the divergence is, but in this case, over the boundary, we can actually arrive at the boundary conditions for the electric field and the magnetic field, and the corresponding boundary conditions for the potentials. So let's see if we still remember those. And so let me just give you a minute to think about it. What are basically 4 boundary conditions that you need to know. So this is for the electric field, this is for the potential, the scalar potential, the magnetic field, and the vector potential. Give people a minute to think about, to see if you can recall the boundary conditions. Okay, minute is up. So who wants to give it a go? So the electric field. What is the boundary condition for the electric field? Anyone want to give it a crack? Okay, feel free to type it in the chat box, turn on your mic and speak, that's fine. So maybe let's start with something simpler. In what direction is there a discontinuity in the electric field? Is it perpendicular or is it parallel to the surface? Anybody? Okay, if not, then I may as well give the answer. Again, I do hope that those who are participating take an active role in trying to recall these things. It helps so that you don't have to study as hard during or right before the exam. So for the electric field, we actually have that the electric field above minus the electric field below equals to surface charge over epsilon naught in the direction of or in the direction normal to the surface. So by virtue of that, the parallel component equals to 0. So the parallel components of the electric field do not go into a discontinuity. But when we have an electric field normal to the surface, then you'll see that that actually has a discontinuity. And this is something that we will take a closer look, or we'll see another example later on towards the end of this lecture. Okay, the scalar potential, so phi again above minus phi below can be shown to be 0, meaning that the scalar potential does not go into discontinuity as we cross the boundaries. So this is actually useful. This is good, right? That means that when we when we go through the route of calculating the scalar potential, we don't necessarily need to worry about the conditions on the boundary. Well, you have to worry about it, but not about any discontinuities, whether you're right below or right above. Okay, the magnetic field is a little bit more complex. So the magnetic field above minus the electric field below, given by mu naught. And here we have K, which is the direction of the surface current density, and then cross and hat, again, which is the vector pointing normal to the surface. Okay. Now, if you take the cross product rule again, we have that use the right hand, we go from the K vector. So let's assume the K vector is in this direction and normal is this direction. So if this, then my thumb is the K and my index finger is the cross, then we're doing this crossing like this, and so the field points into your screen right now. Okay, so my middle finger would then be the direction at which the discontinuity is. Now, something that I didn't explicitly show, but that I'll give you here, is that the vector potential above minus vector potential below is also zero, meaning that these both the scalar potential and the vector potential are continuous across the boundaries. Okay, so this is a slightly longer recap than last time because it's been a while since we did this. Okay, so what we want to do now, or what I want to do now next, is to actually now take you into the first method. So this chapter that we are doing here is on solving the Poisson equation or solving the Laplace equation. Okay? In particular, right now we focus on the Laplace equation because that's a homogeneous equation, so there's no source term, and so we have that nabla squared, the Laplacian of some field equals to 0. And the first method that I want to introduce is the so-called method of images. Method of images, as the name will say later on, is actually something where what we'll see is we end up being a little bit creative, putting different images in places in order to create our solutions. And the reason why this works is the first thing that I want to discuss today, and that is the so-called uniqueness theorem. And so what we're going to do now is we're going to prove 3 theorems. Okay? So we're going to prove Green's first theorem, Green's second theorem, and then the uniqueness theorem. And once we're there, we can actually use the uniqueness theorem to construct our first way of solving Laplace equation or solving the Poisson equation. Okay, so I hope people are ready, and then we can more or less get going. Okay, so the first thing I want to do is prove a relatively simple, actually 2 relatively simple theorems, and these are the so-called Green's theorems. Green's theorem. Let's take a look at the first Green's theorem that I want to prove. So I hope everyone remembers the divergence theorem. Okay, so the divergence theorem or sometimes we call this Gauss's theorem. Gauss's theorem okay, I'll get to this question in a moment. So we have, let me write down Gauss's theorem first before I go to it. So for example, if I have that the divergence of some A integrated over some volume, this is the same as A over some surface. In this case, where S and V. So S is the bounding surface of the volume V. Okay. Okay. Now let's put this quickly on pause because there's a question from Pun Chi. Anyway, and he asks, why is A above equals A below, while B equals the curl of A? Doesn't that kind of contradict B above is that? Well, I mean, the short answer is no. And I'm trying to see if there's any good physical way of showing this to you. Okay, yes, okay, maybe there is. Okay, let's see if I can do this. So imagine I've got a function like this. Okay, goes like this, and then goes like this. So in this case, what I have is that the function itself is clearly discontinuous. Okay? But if I draw the derivative, okay, this is a particularly bad one, but you know, the derivative is simply 0 everywhere. And so, whether, even if the derivative, right, curl is more or less just a special derivative, so it is possible to make a derivative of something discontinuous, even though that the actual A itself, the field itself, is not. Okay, so that's more, a little bit more kind of physical sense, but it's something that I do hope that as we go through examples of A and B, that you can go and check for yourself, just by hand, to actually prove that you can show that this is the case. Okay, does that answer your question? This is not exactly analogous. All that I'm trying to show or express is that it doesn't have to be that the function and its derivative are necessarily either both continuous or both discontinuous. So in this case, this is not the exact analogy, because in this case it's the derivative that is continuous, but the actual function itself is discontinuous. But all that I'm trying to express is that they don't need to be both continuous or discontinuous. So Pun Shen Chi, I hope this answers your question. The derivative is not continuous, but the original function is continuous at some point. Okay, so do you mean that the derivative is not continuous? The original function is continuous, but not smooth. Let's see. You're saying the derivative is not continuous, but the original function is continuous, but not smooth. Yes, I think that is correct. But let me come back to this at the end of the lecture. What this exactly means, because we're talking about the curl, not just simple functional derivatives. this case. So it's a little bit more difficult because we're talking about fields, the extent that a field ends up curving. So I need to think whether what you're trying to say, the analogy on this functional form works or not. Okay, but let's do this at the end of the lecture. Is that okay? Just stick around, hang around, and we can discuss this. Excellent. Thank you. Okay, so let's see where we're. Okay, so we want to prove Green's theorem, and so first step is divergence or Gaud's theorem, right? This is something that we by now hope. I hope that people are familiar with. And so what we're going to do is the following. Okay, we're going to consider two scalar fields, one phi and one psi. Okay? And again, under the usual assumption that they are continuous and differentiable in some volume. Okay, there's always this big rant about mathematicians needing to decide everything. If I'm going to use these, then they exist, and if I use its derivative, then the derivative exists. Okay, that's the assumption that we do. And so if we now apply divergence theorem, but on the following form, okay, so I'm taking the integral of phi and then the gradient of psi over some ds, and by divergence theorem I can write that this is the integral of the divergence of phi gradient psi over some volume. And I can further rewrite this because now I take this divergence as more or less the product rule. I write this out and I end up with an expression that goes like this: phi second derivative of psi plus the gradient of phi times or dot product with the gradient of psi. Okay. So this here, it's a very simple proof, but this here is Green's first theorem. Okay, so this was a relatively easy step. So all that we did is we considered two scalar fields, one phi, one psi, and then we take, integrate this over a particular surface. We use the divergence theorem to rewrite this as the sum of two things. Okay. So now let's take a look, and let's take a step further, and let's take a look at Green's second theorem. So indeed, now what I can do now is I can reverse the roles. I can reverse phi and psi. So what do I get? I get that the integral of now psi and then the gradient of phi ds equals 2. And I'm just going straight down to the result. So this is psi Laplacian of phi plus the gradient of psi dot product with the gradient of phi over some volume v. Okay, so now once I've got that, I also take the subtraction, take the difference, between the two results. So the one on this page, I take difference between this result that I've got here with the result that I've got here, and I take the difference. And so indeed, what I can write now is that the integral of phi gradient of psi minus psi gradient of phi integrated over some surface equals to, and of course now what we see is that if I subtract now the right hand side, taking this side, well, let me write this out there. So now what I have is that this is the integral of, let's see, the first one. So in this case, this is phi, second derivative of psi plus phi psi with a dot product minus phi second derivative of phi minus gradient of psi and phi dot product fashion. Okay. And so indeed, what we see is that the product between the gradient of psi and the gradient of phi appear twice. So if you take the difference, that cancels out. And so indeed, we arrive at the following. Integral of phi and Laplacian of psi minus psi and the Laplacian of phi over some volume. Okay, so this here we've got Green's second theorem. Okay, so we're now almost there. Okay, but I'm gonna leave it with a cliffhanger that we're gonna go for a quick break. So it's 5:05 now. Let's come back in 5 minutes, 5:10, and then we're gonna continue showing the so-called uniqueness theorem. Okay, so I'll see everyone in a moment. Ricky, what do you mean? A second monitor in vertical. I'm not sure that I know what you mean. I actually have more than 2 monitors in my office. For those who are interested in seeing, let me show you. I thought I showed everyone my setup, but it's fine. Let me show you. Okay. So it does require some. See, this is the first monitor. Finished. But now here comes the good thing. This is my second computer. Actually, this here is the screen that I write on. This is the second screen. This laptop actually has 2 screens where, I can actually see my notes. So this is my setup, and then this is the microphone. Of course, I am using a little bit of a headset, noise canceling headset, to do this. So yes, two devices, I would say, but 3 screens for teaching. Actually, that's why I love this device so much. Okay, that's good. The notebook is pretty okay, but it's something that the typing, like that keyboard, turns into a virtual keyboard, and then the typing you have to do on a virtual keyboard, which is not ideal. But it's a very good device to just take along trips and to work in the office, to take notes, to read papers and everything. I'm actually waiting for one because this is an e-ink display, so it's not as good as a normal LCD. I'm waiting for that version where there's just 2 displays to come out. It's a little bit like I think the Microsoft Surface Duo, for something like that to come out. But even for teaching, it's actually very useful to have just 2 screens propped up. So actually, this screen, the big screen that I have to have to keep it on, but because it's tied to a wired internet, I prefer to use the microphone here and the screen sharing and everything, or the webcam and everything, just on a more stable connection. Okay, let's go. Let's continue, and let's let's take a look at the so-called uniqueness theorem. So the uniqueness theorem is actually a very, very powerful thing. And let me just first write down the more or less the mathematical description of the uniqueness theorem, and then I'm going to write it down in layman's terms, okay, so more understandable to physicists. So the uniqueness theorem pretty much states the following: if phi, the field, is real, and its first and second partial derivative are continuous, in a region V, and on its boundary S, and, okay, this is what I mean with, this is how mathematicians talk, and that the Poisson equation, okay, where in this case I've absorbed all the constants into rho itself. Okay? And so where the Poisson equation holds, and, okay, another and, phi equals some f, or that the directional or the normal derivative of phi equals g on the surface S, where rho, f, and g are prescribed functions. Prescribed functions. Then, okay, we finally get to the then. So all of this from here all the way to here is the if. Then phi is unique to within an additive constant. Okay, so this is the uniqueness theorem, more or less in its most glorious, verbose, mathematical form. Now let's dissect this. So what does this actually mean? Okay, so it says that if phi is real, okay, so that part is fine, right? So we're not dealing with a complex scalar field. So if phi is real, and its first and second partial derivatives are continuous in the region V and on its boundary S. So basically that the first and second derivative exist and are continuous. There's no sudden discontinuity in the function or in the field phi itself and on this boundary. And of course, in this case, our specific function that we look at is or equation that we look at is the Poisson equation. So that's the second and. So the Poisson equation must hold. And, okay, and this is the point where we actually specify the boundary condition, so that either phi equals f. In this case, at the end, we say that, you know, f is a pre-described function. So phi equals f, or that its normal derivative is g, right? Or again, a prescribed function on the surface S. So basically, this says that, you know, either phi is determined on the boundary, or that its derivative is determined on its boundary. Those are the boundary conditions, right? So that's the and, that's the or boundary condition. And of course, in this case, in the Poisson equation, rho, which is the source term, is known, right? You know the source term. So once all of these conditions are met, then phi is a unique solution within an additive constant. Okay, this is a mouthful, and this is the mathematical description. But in layman terms, okay, in layman's term, what does this mean? Well, it means that if one can find a solution that matches the boundary conditions, boundary condition, then the solution is the only possible solution. Okay? And this is where the power comes from. So once, okay, if for whatever crazy way, right? I close my eyes. I just see a possible solution, and I know that matches the boundary conditions. I'm done. Done. Because, as the uniqueness theorem states, that is the only, right, the unique solution. And this is what is so powerful about the uniqueness theorem. It basically says that if you find a solution that satisfies the boundary condition, and of course satisfies the Poisson equation, then you're done, because that's the only solution possible. And to maybe give a little bit of a sense of what that means before we look at the actual theorem and we actually look at a specific example, let me, at least from a more physical perspective, try to convince you that this is something that this is indeed something that makes sense. Okay, so remember when we looked at the one-dimensional Laplace equation. This is more just give a title. So just recall 1D Laplace equation, which basically says that partial phi d equals 0. And so this, we have a solution of the form that phi is just mx plus b. Okay, a straight line. And so even when I specify the boundary condition so that m and b are specified, I'm still left with a straight line. So graphically, we can think about it in the following sense. Specify some axes. Even when I specify, let's say here, the value here and here, then the solution is in the form of a straight line, right? The solution is simply something that does this. The Laplace equation, especially in one dimension, does not then allow the solution to do this. Okay? Because this would have been an equally good, from a boundary condition perspective, would have been an equally good solution, right? I match the blue dots, the two dots, and I can do anything in between. But we see, right? We see here also a little bit more tightly. By dx squared. So even under this assumption, so once, this is a little bit the uniqueness here. Once I've specified the edges, the boundaries, then the solution is unique in this 1D case. And in order to do that, we basically must have that the solution is the most straightforward. I'm going to put air quotes because, for lack of a better word, is the most straightforward thing you can do, which is the straight line, right? And not this wiggle thing that you see in red. And even if you think about it in 2 dimensions, and then even if you're really that good in 3 dimensions, you can imagine that this would equal to something that, let's say, I've specified the boundary condition here. Okay, so this is some. Then what ends up being the solution is just the 2-dimensional equivalent of a straight line. So let me see if I can give a more or less kind of like a 3D picture. Imagine that this here is the surface that I've defined. And then the actual solution is just a more or less a tense flat sheet that then covers the the boundary in blue, right? So this is a two-dimensional thing. So I've got a two-dimensional boundary, and then the solution, the function itself, should then be something that lies nicely kind of flat on this rim. And so it wouldn't be something that then looks, you know, something that goes maybe a bulge like this. Okay? I'm very bad at drawing three-dimensional things. But it wouldn't be something that looks like this. Okay? This would be the surface. So in other words, it's the most relaxed solution. It's a little bit of a chicken and egg. It depends on how you want to see it. But the fact that there is a uniqueness theorem basically means that, you know, we are looking at the most relaxed solution of this second-order differential equation. That's what it means for the uniqueness theorem, which basically then states that we only have one solution, which is typically the most relaxed solution. And so indeed, you know, once I've specified it on the boundaries, there's nothing strange that could happen on the edges. Sorry, in the middle. Like once I've specified the edges, there's nothing strange that happens in the middle. So one thing that I want to, you know, ask now is the following question. Okay, I'll give you 2 minutes to think about it. Where are extreme values of, you know, my scalar function if it satisfies the Poisson equation? Where are the extreme values? Sorry, Laplace equation. Where are the extreme values? Okay, 2 minutes to think about it. We'll come back in a minute, 2 minutes to discuss this. Okay. Okay, let's get back. I see that Simon has said that the extreme values are on the boundaries. Good. Harry makes a little bit more of a detailed clarification. He says that either at the boundary or constant value all over the bounded area. Okay, perfect. Both answers are good. With Harry's being a little bit more precise, but okay. But I think both of you understand what's going on. So indeed, because we have the most relaxed solution, right? That means that there's no local optima that is not on the boundary, right? So this red surface, this little thing that sticks out, wouldn't be possible because it's not the most relaxed solution. And so indeed, right, it's a consequence of it. The consequence of the Laplace equation, but you know, and it's therefore that you can then specify the uniqueness theorem, because once you know the boundary, know that the solution on the inside is the most relaxed solution. Anyway, good job, Simon. Good job, Harry. And also, you know, thank you so much for participating. Okay, now we're going to do this in 2 steps now. Okay, so first we're going to take a look at the proof of the uniqueness theorem. Again, it's another way for us to be able to, you know, do the manipulation of fields, of the fundamental theorems, right? Divergence theorem, Gauss's theorem, and Stokes' theorem, just to see kind of how we get along with things. Okay, so in order to prove the uniqueness theorem, the first step that we do is actually the following. So let's suppose there are 2 solutions, phi1 and phi2. And both of them satisfy the boundary conditions, okay? And Laplace equation, of course, and the Laplace Poisson. Okay, so what we're going to do is the following. We're going to show that, you know, we're going to consider 2 functions, okay, 2 fields that both specify the conditions that I've outlined in this uniqueness theorem. And we're going to now take a look. We're going to consider difference. Consider the difference. I'm going to give this a symbol chi. So chi equals to phi1 minus phi2. So, okay, let me specify this to be just the Poisson equation. Let me actually, because or the Laplace equation is just the subset of the Poisson equation. Okay. Great. So now that we've considered the difference in that we call chi, then we can we can actually know a property about chi, about difference. Can anyone guess what equation this difference function chi, what it satisfies? Good. So Alex says Laplace of Poisson equation. Well, I mean, more precisely, it is the Laplace equation, right? Poisson equation is typically the one where there's a source term, and then Laplace equals to 0. So indeed, this here must, you know, must adhere to the Laplace equation simply by the following virtue, right? Because we have the nabla squared for chi, which is simply the nabla squared of phi1 minus phi2, equals to the Laplacian of phi1 minus the Laplacian of phi2. Of course, we know that the Laplacian of phi1 equals to rho. Okay? And again, we've absorbed all the constants like epsilon naughts and stuff into the source term. But I also know that phi2 equals to rho as well, which is indeed what we set out here. Because here we've set out in the conditions that the Laplacian of phi equals to rho, where rho is a pre-described function. Here we have this. So indeed, what do we have? We have that this is rho minus rho equals to 0. This is the first step. This chi satisfies plus. Theorem. And now let's take a look what we can do now. Again, here's the uniqueness theorem. So we've now identified that this chi, this difference, specifies the satisfies the Laplace equation. Okay, so now let's take a look, and we use Green's first theorem. Green's first theorem. Let me show Green's first theorem. Okay, so we're going to take a look at this one equals to this one, right? That's Green's first theorem. But instead of looking at two different fields, we're actually going to consider the same field, both of them chi. In which case, what we have is integral v chi, the Laplacian of chi, plus the gradient of chi squared over some volume equals to integral of chi, and this is the gradient of chi dotted with ds. Okay, so indeed we've basically applied Green's first theorem, but instead of two different fields, we consider that phi equals psi, phi equals psi equals chi, basically. So we basically get this equation, but only using chi. Now, this is something that we can now further specify, because if we look at the right-hand side, we consider this side here, then what we're seeing is actually that this is the integral of chi times scalar product of vector field of the divergence of chi at the boundary, at surface S. So let's take a look what we know about this surface. Okay. Because if we go back to the uniqueness theorem, the condition that we've specified is that 1, it satisfies Poisson equation. 2, that at the boundary that I've either specified the Dirichlet condition, which is that phi equals to some f, which is a pre-described function, or the Neumann condition, which says that the directional derivative equals to g, again, on the surface. Now, I've started with saying that the two solutions here, phi1 and phi2, must satisfy the same boundary conditions. Right? and of course the Poisson equation. And so indeed, what do we know about the boundary conditions for chi are the following. Okay? I know that phi1 equals to f equals to phi2, and this is the Dirichlet condition, or that the gradient of phi1 dot n equals to g equals the gradient of 2 dot n. This is the Neumann condition. Okay? And so what I know for the boundary conditions of chi is that chi equals 0, or that the directional or the normal derivative of chi equals to 0. Okay? Because phi at the boundary is specified or its derivative. And so for chi, this basically states that either chi equals 0 or that the derivative, with respect to normal is equal to 0. So this is exactly what we have here, right? This one or this one, either one equals to 0. It doesn't matter which one, right? If chi equals 0 at the boundary, or if the normal derivative equals to 0 at the boundary. No matter what, the right-hand side this here, the right-hand side equals, to 0. So here we arrive at the fact that now we have this phi integral of chi, Laplacian of chi, plus the gradient chi squared, d equals to 0. And let me make sure that I write this again on this page. It's a little bit easier to follow. This plus chi dot chi. Oops. Okay. So now we have that the left hand side, the right hand side equals 0, and we can now establish the left hand side. The left hand side has two terms. Either one term with the Laplacian of chi, and then one term with a gradient squared. The first term, well, what happens to the first term? The first term, we know that the Laplacian of chi equals to 0 for all region, okay? Because indeed we started off saying that the difference, right, if they both hold the Laplace equation, then this equation here for all region P. And so here, what we have here is that what we're left with is that the integral V of the squared of the gradient integrated in space equals to 0. Now, the integrand, okay, it's important to note that the integrand, meaning this thing over here, is positive definite. Okay. So the integrand itself is positive definite all throughout V. So what is the only solution to the equation above? I'll guess it, indeed, the gradient of chi is 0 for all region. Okay, we take one step further, meaning that chi equals to a constant and in the entire region of V. Okay, so this is what we set out to do. We set out to show that under a whole bunch of conditions that I've stated here, that phi, is unique up to within an additive constant. Because I showed that if there are indeed two solutions, then the two solutions, the difference between the two solutions must be a constant. Because in this case, chi is a constant. Okay. Now we can specify this a little bit more. If I have a Dirichlet condition, okay, for the Dirichlet boundary condition, which basically says that at S, I equals to 0, okay, is again phi 1 minus phi 2. Now, if at the boundary the difference equals to 0, but I also know that chi, for all V, chi, equals a constant, not just a constant, it's the same constant throughout V. And so therefore, phi 1 minus phi 2 equals to 0 in all V. So in the case of a Dirichlet condition, we know that there only exists a unique solution. There's not even an additive constant that you can add. Of course, for the Neumann boundary condition, the situation is slightly different. So here you can say that phi 1 differ from phi 2 by some constant. Okay? So this completes the proof of the uniqueness theorem. But again, I don't want to, just prove the condition for the sake of proving the condition. In the end, the power of the uniqueness theorem is, again, if one find a solution. And this is important. By any means, that matches the boundary conditions, then the solution is unique. The uniqueness theorem gives you a free pass, as creative as you want. Just hack together a solution that you know matches the boundary conditions. Then you are guaranteed by the uniqueness theorem that this is the only solution, okay, up to within an additive constant. But we've seen before that phi is simply a potential, right? And so when we actually consider that in its relationship to work, only the difference between, I'm taking a particle, a charge from here to here. The actual constant drops out even when we consider it as a work. Okay? So this is a very good natural point to take a quick break. Okay, 5 minutes. So we're going to come back at 5:55, and we're going to spend the remainder of this lecture showing you the power of the uniqueness theory. And just so that we can see that if I can create a solution, I have the unique solution. Okay, so let's take a 5-minute break, and I'll see everyone in a moment. Okay, welcome back, everybody. Let's take a quick look at Simon's question. Simon's, what is a prescribed function? Um, a specified function. It's a function that is known. Okay. Those who are very interested, pre is before, scribe, scribere, from the Latin, is to write. But it's pre-written. It's already determined. Okay, let's close out today's lecture and see that if we can put the full power of the of this uniqueness theorem in action. And in particular, I'm going to introduce the so-called method of images. Method of images. And it works as follows. So imagine that we are in the situation where I am interested in the following. I have a conducting plane, okay, kept at v equals to 0, and I've got a charge q here. The situation is that I have a charge q, a distance d from a conducting plane. Okay. This distance here, and the question is, what is phi space of, okay? This is the question that then, is a very simple question that we can ask ourselves. So I've got some charge q, I've got some conducting plane, in this case just an infinitely big conducting plane, which is grounded, so phi equals 0. Then the question is, what is phi in the rest of the space? But the problem to solve in this case, okay, so this is even mathematically. Putting it mathematically, what am I trying to solve? Is the Poisson equation. Rho equals to some charge z minus d. Okay? And so the last part here is basically there's a charge q, a point charge, and the location is that you actually use the delta function to specify location, right? So the charge is 0 everywhere except for when z equals to d. Okay, so it's just a one-dimensional delta function that then specifies if, in this case, this is the z direction. This is the z direction. So this is the problem at hand. And you may then ask, okay, so how do I tackle this problem? Well, let's think. In particular, let's think whether we can create a different situation in such a way that the boundary condition, right, that at z equals to 0, phi equals to 0. Like this. And let's see if we can think of something. Let's think see if we can think of a scenario where I would have the same situation where at z equals to 0, the potential equals 0 everywhere. A minute to think to see if you know a possible solution or possible kind of way to do this. Okay, has anyone thought about how to make any situation that you like, where you get z equals to 0 everywhere on, sorry, phi equals 0 everywhere at z equals to 0? Okay, I don't see any answers yet, but let me at least start working towards a solution. So solve another problem. Instead. What is the problem? Well, I've got two charges. One, Q at Z minus D, is the one you originally had. And one at minus Q, delta at Z plus D. Pictorially, this is the situation that we're considering. This is Z equals to 0. I equals to 0 here. Put a charge Q here. But we're also going to put a charge minus Q here. Okay. But we have a situation now where we have two charges. And it's some imaginary line here, phi equals to 0 and Z equals to 0. We can actually check this, right? Because the potential in this case, given by what? Well, phi equals to AE, right? Some constant Q, and then the square root of x squared plus y squared plus z minus, z minus d squared minus Q x squared y squared plus z plus d squared. Okay, so this would be the solution, right? Because I know the potential of a single point charge that's just given by Q divided by R, basically, right? And then some constant. In this case, I've got a negative charge in some other direction, some other place. And so I add them up. This is just a principle of superposition. So once I have these two, I can just add them up and I get the potential of this particular scenario. And here we can check, right? Indeed, make use of high tech. Okay. Okay. So here indeed, okay, we check. So at z equals to 0, indeed phi equals to 0. because in this case, if z equals to 0, what we get is that it's minus d. So this here becomes d squared. This here becomes d squared. Okay? And so indeed, we have the same thing, right? This whole expression goes to 0. This works. And now comes indeed the power, because I know now by the uniqueness theorem, this is the only solution. Okay? So I've created a situation by just adding, by solving a completely different problem, just by adding a charge. Right? So instead of having a conducting plane charge, I'm just saying, okay, I'm going to solve a different problem. I'm going to solve two charges in such a way that I know that the boundary condition is exactly the same. And so whatever solution I get for this situation must also be the solution for this problem. Now there's one caveat. There's one caveat. That is that it's only valid for the upper region. Okay? So the domain of validity of this solution is only for phi equals to for z bigger than 0. Because I know for the other one here, this whole conducting plane, everything below that equals to 0. Phi equals to 0. I know for z is bigger than 0, I know the solution already, which is given by this thing here. So hopefully you see the power of the method of images, right? It's hugely powerful. Okay, now let's consider and let's do some checks. Let's just see if we can convince ourselves that the solutions are correct. Let's take a look at this field, this phi over here, and let's see if it, if it adds up to what we're interested in. Remember the first thing that we did, right? We looked at the boundary conditions for the electromagnetic field. So now we can actually check, because we can also check the boundary conditions. Check indeed boundary conditions. E below is just the negative of gradient equals to 0. Because, sorry, in this case, this is for z smaller than 0, right? Because in this case, this situation over here, this whole space here is kept at phi equals to 0. So there's no gradient. Indeed here, I know that the below is 0. And here, I know that E above minus E below is simply E above, because E below equals to 0. Equals to, and this is the result that we've seen before, sigma over epsilon naught n hat, which is also equals to minus the gradient of phi, in this case for z bigger than 0. So we can actually do this now, because I can now, if I equate these two things over here, then I can calculate the surface charge. Now calculate the surface charge distribution by equating this to that one. And so n hat is in the z direction, right? And so what is this? Sigma here is just given by minus epsilon naught partial phi partial z at z equals to 0. And so phi, since I know phi, right, I know this expression over here, I can take its derivative with respect to z, and then I can set z equals to 0. The solution here is given by the following. So I've got k, I'll write a little bit smaller, try to cram everything in, q z minus d divided by x squared plus y squared plus z minus d squared. This is to the power 3 over 2 plus q z plus d x squared plus y squared plus z plus d squared, all to the power 3 over 2. Okay. On the little curly bracket here. Okay, so this is just taking the derivative with respect to z. And so this must be evaluated at z equals to 0, which in this case is simply minus q d divided by 2 pi yes, if I take out the epsilon naughts, so this is q x squared y squared squared 3 over 2. Okay. This must, let's see, there's another factor minus epsilon here. Okay, so I've just canceled out with the ke, with the constant here. And so I know the surface charge. I've calculated the surface charge of this solution. And in fact, I can now, shouldn't come as a surprise now that the total charge is simply given by q equals to integral sigma ds, right? Just integrating over the entire surface. Well, this then leads to integral of minus qd over 2 pi x squared plus y squared plus d squared over 2. And in this case, I'm going to do, well, I can do the integral. Let me do the integral over some r instead in polar coordinates. So this becomes r squared plus d squared 3 over 2, and then it's r minus r squared dr d phi. Okay. Over the entire volume surface. So the r goes from 0 to infinity, and then phi goes from 0 to pi. Okay. R is bounded by 0 to infinity, and then phi I can do this integral indeed, and I end up with q d divided by r squared plus d squared square root evaluated at 0 to infinity is equals to, anyone want to give me the answer? No, this is fine. If I insert infinity, this goes to 0. If I insert 0 for r, then I get, the denominator is just d squared, square root, which is d. Again, I get q. In this case, I get minus q. But this is indeed, we've checked two things. One, the boundary conditions. Looked at the boundary conditions here. States that electric field equals sigma over epsilon naught n hat. I know phi, so I can calculate phi above, phi below. Okay. Below equals to 0, so there's only an above contribution. And then we use our function for phi that we found through the method of images to then calculate the surface charge, which if I calculate the total surface charge, then that indeed equals to minus q. So let's analyze this problem a little bit more from the physics perspective. The method of images basically states the following. I can put an image, right? I can put a imaginary image anywhere I want in space, as long as I preserve the boundary conditions, right? Now, why are these images like imaginary images? Because they don't actually exist. They don't exist in the sense that, I know that this here, this conducting plane equals to, all the phi equals to 0. But the solution above here is still valid, above z equals to 0. And it will induce a particular surface charge. Okay? And this is what we've calculated here. So it induces a particular surface charge, which equals to, indeed, minus q. The physics here is a little bit as follows. We have some surface, some conducting surface. And indeed, phi equals to 0. This is kept at phi equals to 0. But right here at the surface, we're getting some charge distribution in such a way that this here equals to minus q. So by putting a charge q above the conducting plane, we're causing this conducting plane right at its surface to have some charge distribution where the total charge exactly equals to minus q, which is the situation, the imaginary situation that we put here. But here we've put a point charge at exactly the opposite place here. Right? And so this is just an illustration how you can use the uniqueness theorem and consequently the method of images. By reconstructing whatever situation you have, you can just throw that away, reimagine a different situation as long as the boundary conditions that you've specified are correct. And so by doing this, you are also equipped to tackle other problems, right? You should be able to tackle a problem like this. I give you something that looks rectangle, like this. And here, this is two conducting planes here, and I'm putting a charge Q here. And so I can create the same thing with different images in such a way that as long as I satisfy the boundary condition, then I'm good to go. Okay? Now, the actual solution here is no longer simple one charge that you put. You actually have to end up putting multiple charges. But it's not a problem. As long as I can just concoct a situation that satisfies the boundary conditions, I'm good to go. Okay? And especially for point charges, then by superposition, I can just add all of those potentials up and I have my solution for, again, the region of interest here. These imaginary images, in other places, of course, don't actually exist. Well, they exist in the sense that they live on the surface. They don't live in the bulk. And we've shown here that it actually lives on the surface charge. But, the solution itself is correct. The solution is as if there is an imaginary charge, in this case, right opposite the real charge that I have. That's the power of the method of images. I'll put some exercises in the problem sets for you to practice, for you to just get used to kind of, okay, can I concoct a situation in such a way that I can make the entire surface, or some surface, fix a particular boundary condition. I can just put a particular charge there. So this is, for example, one case here in green that you ought to be able to solve. There are even more complex cases where I can put a ring here and I have a charge, let's say here. Okay. It will require a little bit more creativity, because where do you put the charge? Imaginary charge. And actually turns out it's just somewhere here. The question is just where exactly do you put it? In such a way that everywhere on this conducting surface, phi equals to 0. These are things that you ought to be able to do. Okay? So the exercise class that will show you some techniques, and then we'll give you some exercises for you to practice with this particular technique. Okay? But it's a very interesting way, because you can be as creative as you want. If you can concoct a situation with charges and things, the boundary conditions, then you found a solution. And then point charges are typically the easy way to know the potential. Okay, this ends today's class. Let me open up the floor to see if there are any questions that I'll record. And again, I'll stop the recording if you have any questions that you don't feel comfortable getting recorded. Okay, so for those who want to leave, thank you very much for coming. For the others, please feel free to ask questions. Go for it.
Hello, sorry, I don't understand why in the first part of this lecture, you said that the boundary condition of the magnetic potentials and the scalar potential is the difference is 0, but it doesn't make. I think it doesn't make sense that is 0 is the difference is 0, but when you take the cross product of it or dot product or gradient of it, and it have some value in it.
Okay. Okay, but okay, you do accept that. I mean, we've shown it before for the scalar potential as well, right? The scalar potential is completely is completely continuous. But yes, I know that the electric field is not continuous if I take this component. So let's do this. Right, so this is my boundary, and if I do, for example, this integration from here to here, for example, right, which is just E of L, which is related to phi, then I can show that if I make the boundary just infinitesimally small, this goes to 0. But I've also shown that if I consider this to be some charged surface, right? This is some charged surface, then the electric field normal to this is discontinuous, right? Is related to this. So this is another example where the potential itself, right? Because I know that E equals this. Oops, minus. this. Then also for B equals the curl of A, then it is entirely possible that the effective potential is completely is completely continuous, but that the curl itself shows a discontinuity in a particular direction, of course.
But they are, but if you say that the vector potential are, the difference is 0, so they are, you mean that they are equal, but with you curl of them, isn't they will be the same value? Do you understand? I mean, the A above and A below are equal value, and you take the curl of them, and you're supposed to get the same value. So how come there are difference?
Not entirely sure what you. I mean, let's take a look at, you can say the same thing for phi and the electric field, right?
Yes.
Right. I can take the I can take the values. I can take E above equals E below, and I take the gradient on both sides. You're saying that oh, then E must be completely must be completely must be the same as well.
Yes. Yes.
Right. But as Zhao Feng is also saying, we're looking at the derivative, right? Not the value there. Is the two things may have exactly the same value, but if I take a tiny step, right, from this side or from either side, then they could still point in different directions.
Oh. Oh.
Right? It's the same as if I was saying before, right? I can have a function which looks like this. Or in this case, I can have a function that looks like this. Right? Here, the function itself is continuous. But its derivative makes a sudden jump.
Oh, okay. Okay. It makes sense to me now.
Okay, excellent. Great, thank you. Good question, by the way. No, look, if it's something you don't understand, you ask, right? I mean, that's what we're here for. And there's no stupid question. There's no, we can discuss, we can talk about it, and hopefully I can put a picture in your head that you are comfortable with.
Okay.
I can show you the maths and then everyone can fall asleep. That's fine. But yeah, you can consider it something like this.
Okay. Bye.
Bye-bye. Thank you, Zhao Feng. I appreciate the discussion as well, right? This is good. So, Zhao Feng, are you an exchange student or are you actually taking the 4-year course here? I'm just curious because I don't know how the university handles exchange students in the time of the pandemic, whether they even admit any exchange students. But okay, you're just normal year through. Just curious. I haven't heard any special arrangement. Okay, going once.
Sorry for the method of image. Can you turn to that page first?
Okay, sure. Let me see if this theorem. So this is method of images. So this is the original problem.
Yeah, you said that if we put the conductor for the negative Z region, then we can use the method of image, right?
Sure.
Yeah, but I have a very special question for that. If
Yeah.
we put a positive charge at your location, set equal to dot, and also the same positive charge at the set equal to negative dot position, and the at set equal to 0, we put a conducting plane, very thin plane at set equal to 0, so that at set equal to 0, the potential should be 0. And at set equal to positive dot and negative dot, there are two positive charge. So in this case, can we still use the method of image?
Okay, let me try to see. Let's see if I can understand this properly. Let me open a new page. Okay, so what you're saying is the following. Here, and instead of a whole plane like infinitely depth, you're saying I have a very infinitely thin conducting plane.
Yes.
Which is kept at phi equals to 0. I'm going to put a positive charge here, and then I'm going to put a positive charge here. So that's the question, right?
Yes, thank you.
Okay, so okay, so of course here if I remove this conducting plane, of course, at this conducting plane, phi at this plane z equals 0, phi is no longer 0. Right? That you agree with? Okay, good. So now the question is, okay, can I concoct a situation where I could make this 0? Now I need to be creative. I need to put two charges or more to try to cancel things out at z equals 0. So I could create a new situation where and this is, you know, this requires a little bit of a this requires a little bit of a okay, I see what you're trying to say. Okay, so my first instinct would be, I've never actually seen this question before, but let me see if I could make sense of this. I would say that this charge gets a negative charge exactly at the same point as the positive charge here, right? Because if I imagine this away, if I imagine this top Q away, then I need to put a charge, negative charge Q here. And the same thing goes for this one. So I would put a negative charge Q here. And in this case, let's see, the image charge itself has a um, interesting. How did I solve this? Because this just equals to 0 everywhere. Ah, okay, no, okay. No, this is a slightly different problem. I cannot put an image charge. Okay, yeah, no, okay. Okay. So the problem is that the image charge does not count in this plane here. Right? This image charge does not actually contribute to this plane over here. And so the solution above here is Yeah, it's only as if this charge was present. But of course, this charge here, because of the conducting plane, actually doesn't do anything. You end up with just two regions completely separated from each other, where I just have to put one image charge here. So here, in this top one, we get the usual one that is the same as this solution over here. But then at the bottom one, you get the same, mirrored solution.
Thank you very much.
No problem. It's a good, like, with the method of images is it's much less mathematical. You just have to be more thinking. Okay, how do I get one with the other? Right. So this is exactly what Isaac is saying. With the method of images, the physical charge and the virtual charge cannot coexist in the same region of interest. Okay, but we'll try to cover this in the exercise class where I've shown you the kind of the theory behind it, and then in the exercise class we'll kind of give you some tips and tricks to do the actual questions, and then the problem set will then be there to help you, to give you a challenge to see if you can actually do some of these questions. Okay. Any other questions? I'm going to delete this one. I'll be very confused if they just read this. I'll just leave it. They can look at the recording. Okay, I don't see any more questions, so I'm gonna turn off the recording.